Hello, greetings of the day. This is Dr. Pavitra AC, working as an associate professor in the Department of Computer Science and Design, ATM College of Engineering. Today, I'm going to brief you about the OpenMP program to sort an array on elements using both sequential and parallel merge sort. And also, we are going to record the difference and execution time. First, let us see what is OpenMP. OpenMP is a set of compiler directives as well as an API for programs written in C, C++, and Fortran that provides support for parallel programming in shared memory environments. This OpenMP identifies parallel regions as blocks of code that may run in parallel, and application developers insert compiler directives into their code at parallel regions, and these directives instruct the OpenMP runtime library to execute the region in parallel. What is merge sort? Merge sort is nothing but here we are going to divide and conquer algorithm that sorts the input array by breaking into subarrays until they have one element, and then later merging the results back into a sorted way. The time and space complexities are n log n and O of n respectively, and the sequential merge sort says in C language, this is also a sorting algorithm that follows the divide and conquer paradigm. It recursively divides an array into two halves until the subarray contains only one element. Then it merges these subarrays in sorted manner to produce new sorted subarrays, repeating this process until the entire array is sorted. Let's see what is parallel merge sort. This is also an algorithm that sorts a list by recursively dividing it into sublists, sorting them independently using multiple threads or process, and then merging the sorted sublist. This approach leverages parallel processing to improve sorting speed, especially for large datasets. So here in this section, there are independent block of codes which are able to be assigned to separate threads if they are available. Now let us see the code. In this code we are just including stdio.h, stdlib.h, and openmp.h, and then time.h. These are the header files and macros. The size of the file here, it is defined as 1 lakh. The size of the file may change depending on the larger arrays. And this stdio dot, it is a library file which includes both input and output functions like printf, and stdlib.h, which includes the memory management like malloc, free, and random numbers. This openmp omp, this is a library for parallelization. And time.h, here we are including which is used for seeding random numbers. Now we are going to merge the function. So we are initializing the merge of integer array, integer 1, integer m, and r. Here this merges two sorted halves into array of sorted segment. It divides the array of 1 and r into two halves like left and right. So here we have integers for both left and right. Then it compares the elements one by one. So here it fills the original arrays in a sorted order, and we are using the malfunction mallocation here. So finally it has to free up the temporary arrays. This malloc function in C, this is used for dynamic memory allocation, allowing a program to request a block of memory from the heap during the runtime. So this is in contrast to static memory allocation, where memory for variables and arrays is fixed at compiler time. The purpose is to allocate a single block of contiguous memory of specified size in bytes. So to enable flexible memory management when the exact memory requirements are unknown until the program executes. And then, so we are comparing here. Now we have the merge sort. So in this merge sort, classic recursive merge sort is included, and we are going to divide this into two halves until a single segment remains. So then merge them back in sorted order using the merge sort. So we have the merge sort sequence here. Then we are going to free up this memory size. And later we have a parallel merge sort. So in this parallel merge sort, see here again we are initializing the array size and array, and then for I equal to 0 and less than size with a plus plus. So we are just comparing this random array, random of array size of 1000, 1 lakh. Now it has been initialized to array of I, and then this array of I, it is compared. So it is copied to the copy array, and then finally source is copied to the destination path, and then malloc size is initialized. Now we have got the parallel merge sort and sequential merge sort. In parallel merge sort, we are using OpenMP to create these parallel sections. One thread sorts the left off and the other one sorts the right off. So once both are done, it merges the result. So parallel merge is done. When the array segment is small, that means when the array size is very small, r is less than size, it switches back to sequential mode. So it switches back here into the sequential mode to reduce the thread creation overhead. So normally in practice, as the size as cutoff is often much smaller, like for example 100, for better performance. And next we have got this main functions, and then we are initializing allocating two arrays with a1 and a2 and fill both a1 and a2. So a1 will be copied to a2, and then it measures sequential sort using the OpenMP, and then measures time with the parallel sort, and then prints both the time to compare the performance, and then it frees up the allocated memory space. The here the key takeaways are the threads performance complexity and the use case. So threads under sequential merge, it is a single threaded. In the parallel merge sort, it is a parallel multi-thread. And coming to the performance, sequential merge sort is slower on large data, and parallel merge sort, it is obviously faster with multiple cores. Coming to the complexity, sequential is simpler and parallel is slightly more complex compared to simple sequential. And in the use case, we are going to use small data under sequential merge sort, and large data can be used under parallel merge sort. Now let us see the execution of the programming.